3 and 7.4, which is on circles and ellipses. Last time in class, we did some explorations with relationships of circles and ellipses. So let's just dive right in. So first off, when we first talked about circles, I had you guys tell me the center of a circle who has points at 6, 0 and -6, 0. And most of you were able to figure this out, that the center is going to be halfway between, which is at 0, 0, which is great. Good job. The next part that we figured out was, the next question rather was, find the possible values of m in the point 2m, which is on the circle. Now there are two possible values because if you draw a line straight down, if you have any circle, well, if you have this specific circle, actually let's actually draw a circle. That would work. So if we have a circle, and this circle's at centers at 0, and we're at 6, 6, or 6, 0, and -6, 0, and we were to draw a line at 2, man, this is super awkward. This is awkward. There we go. Alright, that looks better, a little straighter. So we have, if we put a line at 2, let's say that's there at 2, we have two possible points. Here at 2 positive m, and here at 2 negative m. So whatever m is, there's two values for it that we can have. One that's on the positive side, one that's on the negative side. So to find that, we use the distance formula. Since we know our origin is 0, 0, we can find the distance between that point and 2, m. So that's what we did. We found the distance. Now the distance is our radius, and our radius is the same as from here to here. So that's our radius, and since we're at 6, 0, that means our radius is 6. So we're going to use the distance formula, substituting in 6 for our distance. So we know, well, this actually is kind of related to the Pythagorean theorem. It's actually, in fact, the Pythagorean theorem. If you look, we kind of have a right triangle here. It's not exactly on the line, but it's close enough. So our since we know our radius is 6, our radius is actually going to be the hypotenuse of our blue right triangle here. So that's why we do 6 squared equal to the height where the point is, which would be m squared, and the distance along the bottom of the triangle, which would be 2 squared. Now if you did the distance formula, that'd be the same as your radius equal to the square root of m minus 0 squared plus 2 minus 0 squared. And if you just simplify this, you get r equal to the square root of m squared plus 2 squared. And if we square both sides, we get what I wrote, which is the Pythagorean theorem. Now if we want to solve for m, I would do the multiplication of 2 squared and 6 squared, which gives me 36 equal to m squared plus 4. Subtract 4 from both sides, we get 32 equals m squared, which means m will equal plus or minus the square root of 32. So one thing I can do is I can factor this out. So this gives me the same as 16 times 2, oh, excuse me, not 2, yeah, 2, 32, which is 16 square rooted is 4, so this is plus or minus 4 square root of 2. So my values of m are 4 square root of 2 or negative 4 square root of 2. So that's kind of the exploration. We did a little bit more introduction and introductory investigation on that. We noticed that all the points on the circle are equidistant from the center, meaning that if I choose some point on my circle and I look at my center, the distance from the center to any point on my circle will always be the same. And this distance, as you know from geometry, is called our radius. And we designate that with an r. So all those radii are the same. And it's the same distance all the way around. So that's a circle. We then talked about an ellipse. And I had you do a little bit more investigation with the ellipse. I had you take 2 thumbtacks, or I had you take hold 2 ends of a piece of string and put a pencil in the middle of the string and then draw your ellipse using that. And so basically what you get is you get something that looks kind of like this. When you have your graph, you have your ellipse like this, and I'm going to actually move that. So let's say our ellipse looks like this. When you draw it the way I just mentioned and the way we should have done it in class, you find out that the distance from the 2 foci, so to any point you choose on the ellipse, the distance when you add the 2 will be the same no matter what. If I add the 2 red together, I'll get the same distance as from the 2 orange together, or the 2 purple together. Okay, the distance from the 2 foci added to the same point on my ellipse, when I add those together, will be the same all the way around the ellipse. Okay. The other thing that you should have discovered was when you're looking at an ellipse, the distance from the vertices that are on the major axis, well, the distance that's the longest we call the major axis, the distance that's the shortest we call the minor axis. And that length, half of that length is a, so the whole thing is actually 2a. 2 a's together gives me 2a. And going the other direction, this is b, which means the minor axis is 2b, or not to be. And then the c is the distance from the center to one of the foci, or either of the foci. The distance will be the same. And you'll notice that one other thing that we investigated, or that we talked about when we did the exploration, was we talked about eccentricity. And the formula for eccentricity, we use an E for eccentricity. That's going to be C over A. So whatever the distance from the foci to the center is, we divide that by half the major axis, and that's the eccentricity value. Now whatever the eccentricity value is, that tells me how squashed the ellipse is. And if you think about it, eccentricity, what it stands, when you think about the word eccentricity, you think about somebody who's an odd person. But what it really means, what the base root words mean, it means off-center or off-circular. And so that's where we get the squashed term. It's not a perfect circle. And actually, a circle in the investigation, I don't know if we talked about this at all, but a circle is actually a special case of an ellipse. In the investigation, we should have redone our ellipses so that they are less and less elliptical and more circular. So the closer, you'll notice the closer to a circle they are, the closer the foci become. So these are just approximations of where the foci would be, but once it becomes a circle, the two foci actually lie right on top of each other. So a circle is a special case of an ellipse. So we use string and pen to create an ellipse, and what you should have figured out is the distance from each focus to a point on the ellipse will, when we add it together, will be the same all the way around, and the eccentricity will be the same for the whole ellipse, no matter as long as the major axis stays the same and the foci stay the same, the eccentricity will be the same. Alright, so that's kind of what we did in class. So let me just give you a bit of information. So this bit of information is going to be basically some definitions and some other things that we might not have talked about or covered in class. So the first thing I want to say is the definition of a circle. A circle is actually the set of all points on a plane or in a plane that are equidistant from a point, from a fixed point. So if you think about a circle, the edge of a circle is called the circumference. And this circumference contains all the points in the circle. And all of those points, as I said earlier, are equidistant from the center. So the point in the middle is the center, and the distance from that point in the middle to each point that's on the green circumference is the same distance all the way around the circle. And we call that my radius, r. So this is our radius. And for circumference, we denote that with uppercase C. Now, from geometry, you should have remembered that the circumference is equal to pi times your diameter, or since your diameter, once you draw it through two radii through the center, it's equal to 2 radius, or 2 pi r. 2 times pi times your radius. So that's the definition of a circle. Those are basically most of the parts. I can also find the area of a circle. I'm not too concerned about this with this right now. It's just some piece of information for you guys. If I want to find the area of the circle, I multiply that by pi times my radius squared. The next piece of information would be the form of the equation of a circle. And this is, if you remember, we used the Pythagorean theorem to find the equation of the circle from the exploration. Since, let's say my center is at xy, or excuse me, we use hk for our center, and then the point on the circle we say is xy. So to find the equation for that, I would do the distance. Since my distance is my radius, I do my radius equals the square root of x minus h squared plus y minus k squared. Now, if I don't like that square root, I just square both sides, so I get r squared equal to x minus h squared plus y minus k squared. And this is the equation for a circle for any center and any radius. So if the center isn't not at the origin, which is 0, 0, then you can use h and k. So this is a circle. Next, we talk about ellipse. The definition for an ellipse is the set of all points on a plane. So it starts off very similar to a circle, but it changes a little bit, whose distance from two fixed points this time instead of one, and when I add those up, well, two fixed points, we can call them F and G for my two foci. Those are the foci that I'm talking about. Two fixed points F and G add up to a constant. And what this simply means is exactly what I talked about earlier. If I have my two foci, this is F, this is G, and I choose a point on my ellipse, if I add the distance, let's say this is point P, okay, FP plus FG will equal the same number no matter where P is on my ellipse. That's what this definition is saying. Some other pieces of information about an ellipse are the major and minor axis. The major axis is the distance from one end to the other end of the ellipse, and it's actually the longest, well, I'm going to call this the major axis here. But this is my longest diameter. You remember from a circle, the diameter of a circle is the distance from one point of the circle to another point that goes through the center. That's a better bracket or brace. And then our other axis is called our minor axis, and that's the smaller of the two. So this is my minor axis. And this is the shorter diameter. Now the major axis, half of the major axis actually is what I should say, we use the letter A for. So each half is A, so the whole major axis is 2A. And for the minor axis, we use B. So each of those halves is B, so the minor axis is 2B. Now wherever the foci are, let's say my two foci are here and here, okay? Whatever the foci are, so here's focus 1, here's focus 2, the distance from the focus to the center is C. So the whole distance from focus 1 to focus 2 is 2C. So F1, F2 equals 2C. All right. Now, one piece of information that we probably talked about we should have talked about in our investigation is the eccentricity. And the eccentricity of, as I said before, of the ellipse is how squashed, or some teachers say how round the ellipse is. And so, for an ellipse, the eccentricity is always going to be equal to 0 or less than 1. If it's equal to 0, if E is 0, that's a circle. So a circle is a special case of an ellipse. If it's greater than 0 but less than 1, so if E is less than 1 but greater than 0, then we have an ellipse. And there are lots of different ways we can categorize the eccentricity in terms of how to solve for it. But really the most simple is the eccentricity is the distance from the center to one of the foci, which is C, divided by half the major axis, which is A. You can also say that it's equal to the square root of A squared minus B squared, all divided by A. Yes, as you can see, this kind of looks like the Pythagorean theorem. And yes, the Pythagorean theorem is involved in solving for the eccentricity and finding what this equation is. But it's very complex and it's very hard to understand if you don't have a math degree, let alone if you don't have a master's degree in math. So just trust me on this. The eccentricity is equal to C, the distance from the focus to the center, over the distance, half the distance of the major axis, A. Or you can use the square root of A squared minus B squared over A. If you wanted to think about it this way, since they are the same fraction, C is the same as the square root of A squared minus B squared. So really, I could use the Pythagorean theorem with this right triangle I outlined in orange here. So this would be your C. Actually, no. Your C would be this bottom leg, and this is A. So it's kind of complex, but trust me on it. The distance from the focus to that point up top will be A. And so if you did the Pythagorean theorem, you'd have C squared plus B squared equal to A squared. So if you'd solve for C squared, you would get C squared equal to A squared minus B squared. And then solving for C, we get the square root of A squared minus B squared. So that's where that comes from. Now, trying to figure out that A is the hypotenuse and that A is the same distance as the A for the major axis, that is the big proof. Trying to show that they're equal to each other, that is where it's really hard. Understanding why they're the same, that's okay. But trying to figure out why it is that way, that takes a lot of time and effort and understanding that we were not going to go into right now. So just trust me on this, memorize this. You're going to have to know it for the CST. I guarantee there will be at least 2 or 3 questions on the CST about eccentricity, so you must understand this. So the next piece of information is the equation for an ellipse. If you have an ellipse, the general form of the equation is x minus h squared over a squared plus y minus k squared over b squared equal to 1. Now this is for an ellipse going horizontally. For vertically, you would have x minus h squared over b squared plus y minus k squared over a squared. And the reason for this, the difference between the two, is just think about which direction is your major axis. Your major axis is going left to right on the horizontal. That means A value, the bigger axis, is 2A. So half of 2A is A. So that means that this A here is half your major axis. So if you were wanting to graph horizontal, your center would be h and k. Your major axis would be 2 times your a value, and your minor axis would be 2 times your b value. I'll do an example that kind of shows you what this is talking about. And the same thing goes for a vertical ellipse. The only difference is your major axis is going up and down, and your minor axis is going left to right. Okay, I think that's all the information for this section. So let's go ahead and do an example and then give you your short answer questions, or your multiple choice and your free response. So since a circle is very similar to an ellipse, and it's actually the same as an ellipse, just a little modified, I will just do an ellipse as in our example. So let's say I have an equation x minus 2 squared over 9 plus y plus 7, not 4, 7 squared over 16 equal to 1. So this is very nice. It's already in standard form for me. Sometimes they might give us an equation that's not in standard form. It's easiest to put it in standard form and then use that to find where everything would go in the graph. So since this is 9, I can rewrite that 9 as 3 squared. And since it's 16, I can rewrite the 16 as 4 squared. So my HK value, my center, is at 2, negative 7, because whatever the number is inside, I take the opposite of it, and that's my H and K value. So on my graph, if I were to graph this, I have a center at 2, negative 7. So if I go over 1, 2, I go down 7. 3, 4, 5, 6, 7. I need to extend my line a little bit. So my center is right there. And actually, I'm going to run out of room trying to draw this, but we'll see how this works. So then I look at my A and my B. And actually, you'll notice I have 3 here and 4 here. So which direction is this going? Since 4 is the bigger number underneath Y, that means this is going to be going vertical. So what that means is, in the X direction, I'm going to go 3 units left to right. So from my center, I go over 3 units and put a point. And going the other direction, I put a point 3 units to the left. Okay? Then I look at my next for the Y going up and down. So I'm going to go 4 units up and down. Now I can't show you going down, but I will show you going up. So that those points you then put a dash box around. And those points become the points of contact for your ellipse. Okay? Let's see if I can't move this stuff here. I'm going to move it up into my original drawing here so that you can see what I'm talking about. So we're going to go down 4 points. So 1, 2, 3, 4. So then I go down 4 here. So I go down dash here. And let's see here. Okay, so then I would make my ellipse like that, and that's how it's done. I go 3 units in each direction here, and 4 units down and up. That's how you graph an ellipse when it's in standard form. That's as easy as it gets. So here's your multiple choice question. Go ahead and pause the video now. And here's your free response question. Oops, quadratic catic. Let me change that real quick. There we go. Alright, well, I apologize for the length of this video. There's a lot of content in this. If you have any questions, please answer any questions in the form below this video, and have a great weekend.